Hello, my name is Konrad Scroger, and over the summer I studied the analysis of altimetry system error. Before I get into what the analysis of altimetry system error is specifically, first I just want to talk about aircrafts a little bit. So aircrafts, when they're in flight, they have multiple ways to track their altitude and the path of their flight. The two ways that we looked at were through altimeters and a GPS. So an altimeter, the way it works, is it records your pressure altitude, which is based on the outside air density. So for a given flight, the air density may change a little bit, but if it's constant over the course of a flight level, then it will remain constant. The other way that aircraft will track its height or its altitude is through a GPS, and a GPS records the geometric altitude of the aircraft. Now, where the problem with altimetry system error can occur is that the pressure altitude from the altimeter may remain constant over an entire flight level, which just represents a certain interval of flight. And while the pressure altitude may remain constant, the geometric altitude may change hundreds to thousands of feet. Now, this, within this, creates problems because the aircraft may not have an accurate idea of where it is within the sky. Because of this, the FAA, the Federal Aviation Administration, has set restrictions upon aircrafts, which one of the restrictions that they have set is the reduced vertical separation minimum, which is RVSM. This basically entails, is to keep aircraft safe. It basically entails that up to a certain flight level, two aircrafts, they have to maintain a certain distance. So flight level, like I talked about before, it's set up at every 100 feet. So for example, flight level 290 would just be 29,000 feet because 290 times 100. So for normal aircrafts under flight level 290, there has to be an RVSM or a separation of at least 1,000 feet. Above a flight level of 290, the separation increases because of the increased altitude. There is more error in the calculations. So above a flight level of 290, has to be 2,000 feet, unless the altimeter and equipment on the aircraft has been pre-approved, then it is again 1,000 feet. So the point of this research is to try and minimize this error. When we incorporate meteorological conditions into the altimeter, that creates a model for us, and that creates a new calculated height that can go along with the geometric height. And the difference between this geometric height and this new calculated height with meteorological conditions is the altimetry system error. So this is very important because given today's world, there's always increased air traffic, things like that. There needs to be more space for flights. This can allow reduced vertical separation between aircrafts, and this can reduce fuel consumption, make more efficient, more planes in the sky at a certain time. So the way this was done, a big portion of this research was learning and then mastering the programming language R. What R is it's really good at modeling different equations. There's many packages because it's a free community-based programming language. So many of the packages that we use were like R Nomads, which was connected through NOAA, the National Oceanic and Atmospheric Administration. A big portion of that was able for us to use the code in R to pull the meteorological conditions for our code. Another package within R was the elevator package. This allowed us to download data for current elevations depending on what the flight level was. And within R is a very capable language. So for us, we have multiple equations that we can use. They're easy to do by hand, but it takes a lot of time to do specific intervals. So it's 6 hours of flight data for each flight, and we have 6 flights given to us by the FAA. It would take a lot of time for us to do all that by hand. So R is able to do those calculations, and it still has its drawbacks. It still takes a lot of time, but R is able to minimize that time for us and then create a nice graphic to model this path of a flight. So where I came in this project with my partner, Matthew, was between models 2B and 2C. So the big changes between those as a result was a reduced altimetry system error. So the big changes between 2B and 2C was fixing a lot of the problems we had in modeling our loops and our path of the flight. So a big change, we reduced the altimetry system error from about 1,000 to anywhere from 1,000 to 6,000 feet. We reduced it to about 200-ish feet with still some deviations, which I'm going to talk about in a sec. So that was a big change for us. We essentially got to the point where we're modeling our equations correctly. It's just there's still things that we aren't taking into account. So in my report, I showed a specific flight, Flight D, which is one of the 6 flights that we were given. In Flight D, it was hovering around 100 feet as error until a slight deviation once it got to an increased elevation. And from that, we noticed that at higher elevations, the altimetry system error seems to increase. So for future models, that's what we're trying to figure out now. We're trying to move on from 2C to create models that either incorporate elevation more or eliminate them to see how elevation directly impacts our altimetry system error. On top of that as well, our model currently doesn't take into account moisture. It currently just takes air as moisture-free or dry air. I've already been looking into different equations that would take into account like dew point, dew temperature, saturation pressure, things like that, and like the relative humidity, how that might impact the ideal gas constant, how that might change as there's different mixtures at different points in time. Different things we want to look at. We also want to look at GPS error. So as of right now, the GPS, or the geometric height, we currently take that as the standard that we're trying to reach, but there's also error in that. We want to figure out what the error is in the GPS for future models, and we want to be able to incorporate that so that as our model continues to grow and continues to get more accurate, we have a better sense of where in the sky the airplanes and aircrafts really are. Another problem, so the FAA, we received 6 sets of flight data, and this was a lot of data that it takes a lot of time to work through, but at the same time, with only 6 individual flights, there's only so much we can gain from that. So as of right now, we want to be able to find more data. So my partner has been looking into Flight Radar 24. It's a website that looks at currently flying flights and records their altitudes. So we've been looking into using Python to try and record that, get more data, so we can try and create more relationships between the altimetry system error and the things that we are studying. Another thing with R, a big portion of using R was just that it took a lot of time. If we were running even at like 100-point intervals for our flights, it would take up to even like 6 or 8 hours at a time. So another thing that we're trying to work on is finding more processing power to try and handle large amounts of data. Because R, it was really good at handling this data. It just unfortunately takes a lot of time. And time is like the one thing that we're just like missing out on, because we just have to wait for data to run while we're trying like to do other things at the same time. But as of right now, we've noticed that the equations that we use, like use the acceleration of gravity, hydrostatic equations for differential fluids, and as well as the ideal gas law. We've modeled those to as best as abilities we can and gone to a reduced altimetry system error from about 1,000 to within the hundreds, which has been really good. From there, we just want to incorporate improving on the elevation and incorporating better future models. That is pretty much everything I've done in this research over the summer. There's still a lot I need to do, but thank you so much for your time. Thank you for this opportunity.